So what I want to do today is kind of back up a smidge, recap a little bit where we left off, because we were at the end of doing a system analysis problem, but we hadn't quite finished it, and I want to make sure we go through that completely because it gives us a chance to illustrate the process of how we do partial fraction expansion when we're doing it with discrete time Fourier transforms. Turns out it's not the most straightforward place to apply it, but it does still work. We'll not spend a lot of time doing that and doing a lot on methodology for that, because we'll be engaging that a lot more thoroughly when we get to Z transforms. So there'll be many more opportunities where we want to do inverse transforms and that we'll need partial fractions and have a bit more disciplined approach that we can apply then. But I want you to see how it can be done and how we can do these kinds of problems with discrete time Fourier transforms. And the problem that we were approaching was basically a system analysis problem of finding a zero state response of some input for some discrete time system, where that discrete time system now is described by its frequency response, and the input was provided to us in an analytical form. And so we wanted an analytical closed form function to describe our output y of n, which we could have accomplished in the time domain by solving a difference equation or by doing a convolution. What we wanted to illustrate here is that with transforms, it could be potentially easier to do that problem, at least mathematically, where with the discrete time Fourier transform, the problem of convolution turns into a problem of multiplication, which is obviously a bit more straightforward. So to recap the underlying principle here, instead of convolving things in a time domain, we're going to multiply the discrete time Fourier transforms. That will get us the discrete time Fourier transform of the output. We'll have to do an inverse transform to get back to the time domain to get the actual thing we need and want, the output described as a function of n. We skipped through this last time, and worth mentioning that process of multiplication, of spectral multiplication, we can carry out either analytically if we have analytical forms, or we could carry it out graphically as well. If we have x sub f, the complex DTFT of the input signal, and if we had the plot of its magnitude and phase responses, and we had the frequency responses, magnitude and phase, we can get the graphical representation of the spectrum of the output signal by multiplying those two complex functions, which means we're going to take the magnitude responses and multiply them frequency by frequency. So we would take the shape of the magnitude response and all the values of the magnitude response of the, or magnitude of the input spectrum, multiply it by the magnitude response values for h of f, and get the spectrum content magnitude of the output signal. Similarly, because we're multiplying complex functions, we would take the phase angle of the input signal, add to it the phase response of the discrete time system, and the sum of those angles would be the phase of the output signal's Fourier transform. We're going to do that analytically, though, and the process we were following was first transforming the input signal, getting the frequency response somehow. Usually we're going to do that by DTFTing the difference equation and rearranging it, then multiplying those two discrete time Fourier transforms to find the Fourier transform of the output, and then doing an inverse transform to get back to the time domain. We got all the way through step 3 last time. Today we'll recap that real briefly for the problem we were doing, and then try to finish it up with step 4 there, to how we do the inverse transform with DTFTs when we have to use partial fractions. So this was the problem we were solving. We had our IIR system with a difference equation, y of n equals x of n plus 1/2 y of n minus 1. So we had our feedback here. And we wanted to know what's going to happen to the system if I put a unit step in. So we're basically trying to find what was the step response of this system. And so we did that. Let's switch back over to whiteboard to recap what we were doing there. And so we followed along this process. We said that x of n was u of n. We had our h of n. We found our DTFTs of each. We had already previously found our frequency response. And so we multiplied those two together and got some functions that we then found, well, we can simplify the first of these. When we multiply them together, we applied a multiplication property of impulses to see that this whole first term became a big 2 multiplied by 1/2, which left just our delta function, delta in frequency, and we had the product of these two terms, and that's where as far as we got. We said, okay, we now need to take that result and inverse transform it, and pull out our transform table and say, oh good, we've got a transform and inverse transform for delta sub f, that's 1. But this quantity, this product, there was nothing exactly like it in the DTFT transform table. And so we had to try to break it up into terms that do appear in the transform table. And each of these individually do, but the product of them doesn't. And so that's why the next logical step would be to break these two up, this product, into a sum with partial fractions. And so that's what we'll pick up with today. And so to break that up into partial fractions, well, we can keep the delta sub f. We don't need to break that up in partial fractions. But the other one, we will. And we have two terms in the denominator. So we would have two partial fractions with some unknown coefficient in the numerator. And in the denominator, we have the first term, 1 minus 1/2 e to the minus j2 pi f. And in the other term, some other unknown k2, 1 minus 1 e to the minus j2 pi f. So we're just saying, if I broke this up into a sum, what values would I need for k1 and k2 for this to be equivalent? And if I want them to be equivalent, well, I can recombine these under the same common denominator as these, so we have a basis of comparison. And so still have our delta sub f. And if we put these under the same common denominator, and since we're multiplying these together to get the same common denominator, what I'll have is the k1 times this denominator term added to k2 times that denominator term. So k1 times 1 minus e to the minus j 2 pi f in the numerator, plus k2 times 1 minus e to the minus j 2 pi f. And if they're broken up that way, then these are the delta functions are certainly equal. They're under the same denominator. And so I know that whenever this quantity is that I've just written out in the numerator, it has to be equal to the numerator here. It has to be equal to 1. And so let's multiply these through and get a k1 minus k1 e to the minus j 2 pi f added to a k2 minus a k2 e to the minus j2 pi f. And that has to be equal to 1. And now, okay, I've got a real valued 1 on this side. So I see a couple of real valued things, but I also see some exponentials over here on one side that I don't have on this side. So just to remind myself that I've got to have an equivalence here, I'll say this side is 1 plus no e to the minus j2 pi f's. And that provides me a clear path to get two different equations with two unknowns here. The real values have to add up to 1. The ones that are multiplied by exponentials have to add up to 0. So we have our two equations that come out of that. K1 plus K2 has to be equal to 1. And the other two factors here have to add up to 0. So that's a minus K1 minus 1/2. And we lost a 1/2 somewhere. When we multiplied our K2, you let me get away with that. There's a 1/2 in there, right? Because we're multiplying our K2 times 1 minus 1/2 e to the minus j2 pi f. And so that term, the K2 minus K2 times 1/2, that has to be equal to 0 because I don't have any exponentials terms on this side. That tells me that if I add these two together, 1/2 K2 must be 1. So therefore K2 must be equal to 2. And if K2 is 2, plugging that back into one of these equations, we see that K1 then has to be minus 1. So we have our two partial fraction terms. So recapping then, we have our y of f is a delta of f. So negative 1 over 1 minus 1/2 e to the minus j2 pi f added to a 2 over 1 minus e to the minus j 2 pi f. And now if we look these up in a Fourier transform DTFT table, we would say, yes, I've got an inverse DTFT for a delta function. That's okay. I have an inverse DTFT for this function. And this one, well, this one, I do have something like this that's a DTFT. And it's the one we use in the forward transform of u of n goes to a 1/2 delta of f plus 1 over 1 minus e to the minus j 2 pi f. I have 2 over that denominator. So it looks like it's a 2u of n, except I need a 2 deltas, a 2 over 2. Oh, I need 1 delta of f to accomplish that. And fortunately, I do have that. I have a delta here, so these two actually will combine to give me a 2u of n in the inverse transform coming from this piece and this piece. And then this piece inverse transforms to simply a minus 1/2 to the n u of n. Okay, so that would be one approach to using partial fractions, probably the most straightforward approach with these DTFTs. Now, the good news is it's actually going to be more straightforward with the Z transforms. We're not going to have all these e to the j things floating around. And so we'll spend more time on it then, but did want you to see that it can be done. I can also make an interpretation of this output that we got. And remember, this is a zero state response because effectively we've done a convolution here. And so if it's a zero state response, I should be able to see a forced response and a natural response. Our input, x sub n, was a unit step. And so we recognize this first term here has the same functional form. So that's likely to be the forced response piece, leaving the 1/2 to the n u of n to be the natural response piece. Okay. And so again, we could do this system analysis and get closed form analytical solutions, get complete zero state responses. And so let's be explicit about that. This is a zero state response, the system, because we found it by convolution. And of this problem, probably the hardest part was this section, this inverse transforming by partial fractions. But if you're good at partial fractions, that's not too challenging. It's all algebraic. We don't have all the flipping and shifting and other things that convolution requires. We don't have all the long, laborious steps of solving a difference equation. And so hopefully you're getting the impression that doing these things in the transform domain is going to be better and will make it even more useful when we get to Z transforms, because both the complex exponentials are hidden in that case, and the Z transforms will have the advantage that using the one-sided Z transform will actually be able to do the complete solution, the total solution, including the zero input response, which we can't do with the DTFT. So what good is the DTFT? Really, what's it good for? Well, its best job is the previous one we did at the end of last time, finding steady state responses to sinusoidal harmonic signals, even harmonic discrete time signals. That's what the frequency response is really descriptive of, and gives us a very straightforward way to determine those responses for those kinds of inputs. It also has it helps us to analyze and understand what's going on in our signals as we apply various kinds of techniques and processes to them. And the rest of what we'll be covering today is probably a good example of that. So if we were to actually plot that result, here's what it would look like. We took our unit step in blue, went from zeros prior to n equals 0, and then ones from then on. The system responded, started out relaxed, so it was at 0, and then it jumped up to 1 and kept rising, following that 1/2 to the n u of n exponential until it came up to the value, its steady state value of 2. Okay. The other thing that the DTFT is good for is helping us to revisit some sampling rate issues, some things that we tried to understand and explain in terms of the analog frequency domain. But after we sample a signal, we have it in the discrete domain, and so we'd like to understand these issues from the standpoint of the DTFT and the digital frequency domain and how things are carried out there. And the two processes we'll want to look at first are increasing and decreasing the sampling rate, decimation and interpolation. And then finally, we'll look at what happens when we window or truncate functions in time, what happens in the frequency domain, and the DTFT will give us a good description of that, the process we'll call windowing. So first, downsampling. This is something you probably have been encountering in your EE368 labs on sampling. And this is engaging what happens if you've already sampled a signal, but you want to reduce the sampling rate of this signal to a different rate. And we use this symbol with the downward arrow followed by a D, where the D tells us what factor are we downsampling by, what factor are we reducing the sampling rate by. So if our input signal is some sampling rate, we'll call it fs old. After I go through the downsampling process, I'm going to divide this sampling frequency by D, and that will become the new sampling rate for the output of the signal. So it should have the same basic shape, just fewer samples. So downsampling reduces the sampling rate by some factor, and we accomplish it in the time domain literally by retaining only the right samples and skipping or throwing away a fixed number between each of those ones we keep. So for example, if we wanted to downsample by a factor of 2, we keep a sample, throw one away, keep one sample, throw one away. So throw away every other sample, and then we will have effectively have the samples that would have occurred if we had started out with a sampling rate that was half as fast as what we actually used. If you wanted to downsample by a factor of 3, for every sample we keep, we would throw away 2, and so on. So keep one, throw away 2, keep one, throw away 2, and that would give us, again, a signal that appears exactly like it would have if we had used this lower sampling rate at the original time back at the A to D converter. Now, so that's what we're trying to achieve. That's what we should achieve if we're doing this just by throwing away samples. We should come out to be looking exactly like we would have looked if we had originally had this lower sampling rate. What's going on in the frequency domain, and we looked at this briefly with sampling, is if we use an analog frequency axis, we start off with some function with some band limit, and we sample it at some other sampling rate that maybe we determined was higher than we really needed, and we want to use a lower sampling rate. We know that the original signal spectrum is going to be replicated around every integer multiple of the original sampling rate. When I throw away those extra samples, that remaining set of samples look like, and their spectrum should look exactly like a signal that was sampled at that lower rate, at that new f sub s new. And so now around every integer multiple of that, we should have a copy of the original spectrum, of the original signal. And so we'll cram in more copies in the analog frequency range when we have that lower sampling rate. Now that's what that looks like from the standpoint of analog frequency. In the digital frequency domain, I don't know anything about sampling rate. My sampling rate is always 1. And so when we change sampling rates, we change what the spectrum looks like sandwiched between 0 and 1. So if this was our discrete time appearance, our discrete time, our DTFT spectrum of that original signal at the original sampling rate, over here we have again our original signal. We have our spectral copy at 1. We have another one at 2. We have it -1, -2, and so on. Now, when I downsample to a lower sampling rate, that lower sampling rate that was previously somewhere in here, that now becomes frequency 1. And so in the range of digital frequencies, it looks like I've taken my spectra and expanded them, stretched them, but stretched them towards the Nyquist frequency. Like we've taken both of these and tried to squeeze them in towards the middle. Same thing here. We've taken these and squeezed them in towards 1/2. What we've actually done is change where that sampling rate is, and put our new spectral copy in and rescaled the axis. So in the analog domain, it looked like we put more copies in between. In the digital domain, we still only see these first copies, but now they're getting closer and closer together. So it appears like our DTFT spectrum was stretched inward towards the Nyquist rate. Now, there is, of course, a limit to how far we can downsample, because in the analog domain, these spectral copies now are jumping in closer to each other, and we're getting more of them. What's going to matter is, what is the bandwidth of the original signal, not relative to your first sampling rate, but what is it relative to the new sampling rate? Have you followed or violated the Nyquist criterion for the new sampling rate? If you have, if your new sampling rate is not twice the band limit on your signal, you will have aliasing after you downsample that you didn't have before you did. So aliasing can happen in the downsampling process. So if you want to make sure it doesn't, we have to make sure the Nyquist criterion is followed relative to the lower the downsampled sampling rate. So here's an example of a signal that's not terribly band limited. It's a causal exponential signal. Happens to have this magnitude response. If I take that bunch of samples and I downsample it by a factor of 2, so I throw away every other one, then I'm taking my spectral copies and move them in towards 1/2 there, and we see we're going to get more overlap, more aliasing going on than we had originally. And if we downsample yet again, we're going to make copies of the center spectrum and bring those in even closer, and we're going to get even more overlapping and aliasing going on. So if we if we've done an okay job of sampling in the original case, and in this example, our sampling rate is set at 6 times the band limit of our signal. So we're oversampled very nicely. We've not violated the Nyquist at all. If we downsample this by a factor of 2, that's okay, because in the new sampling rate, we're now no longer 6 times the band limit, but 3 times the band limit. And so we still get separation between our spectral copies. But if I were to downsample by a factor of 4 from my original signal, then the upper limit, the band limit of my signal, is now only at my sampling rate is only 1.5 times that upper band limit, not 2 times. And the spectral copies now are going to start overlapping and give us some aliasing. So downsampling can create aliasing if you have violated the Nyquist criterion for the lowest sampling rate. That's why we distinguish two processes for downsampling. Downsampling usually implies exactly what we've just said here, throwing away some number of samples and just creating a signal that looks like it was sampled at a lower rate. Decimation is intelligent downsampling. It's downsampling where we add an additional step to make sure that aliasing doesn't happen in that process. So we effectively prevent it from happening, even if it means we're throwing away some of the signal content. So before we downsample, we band limit the signal that we're going to downsample to a Nyquist rate that's appropriate for the new downsampled lower sampling rate. That means we've got to put a low pass filter before the downsampling process. In this case, though, we're not talking about an analog filter. This is a digital, a discrete time filter, because we've already got a sampled signal. So we'll take that sampled signal, run it through a digital low pass filter that band limits it to 2 times the new, or to 1/2 the new sampling rate. Then do the downsampling of the signal to the new sampling rate. And so if we even had a case that like this where we were going to get aliasing when we downsample, instead of allowing that to happen, first we take a ideal low pass filter and cut off the parts of the signal spectrum, the discrete time signal spectrum that could potentially alias, then go through the downsampling process and have a signal that well, we had to throw away some information to prevent aliasing, but we have prevented aliasing. We prevented information from encroaching in areas that it would be potentially corrupting. So this is in general preferable to give up some high frequency content as opposed to letting aliasing happening and perhaps corrupting some critical frequency. So that's the difference between decimation and downsampling. Downsampling is simply throwing away samples. Decimation means we're going to pre-filter it so that no aliasing happens in the process. Now, what if we want to go the other way? What if I already sampled a signal and I wish I had a higher sampling rate, but I can't go back and resample the signal? So effectively, we need to create some new samples that didn't exist before. So what we're faced with is actually a challenge of interpolation, as I'm going to invent some sample values, but I want to invent the ones that would have been there if I had sampled at a higher rate. Part of the way we do that in discrete time systems is using a process called zero insertion, or zero stuffing, as some books call it. And as the name implies, it's literally in between the samples that we have already, we're going to stick some additional zeros so that we end up with the right number of samples for the sampling rate we want. So kind of opposite of the downsampling process, zero insertion means if I want to double the sampling rate between every authentic sample I have, I'm going to put in a zero. If I want to triple the sampling rate between every sample I have, I want to insert 2 zeros, and so on. Now, what does that do to the frequency spectrum? Well, here's the spectrum of our original signal. And here's what the spectrum looks like when I do this zero addition. It's like I've changed my sampling rate, but what I've done is taken the whole frequency spectrum and compressed it inwards in the discrete time frequency domain. And so in this original signal spectrum that repeats every integer multiple of 1, that when I went to twice the sampling rate, that first peak at f equals 1 now occurs at the Nyquist rate at f equals 1/2 and minus 1/2. So I've squeezed everything in. So that's not going to give me exactly what I want. What I would like for my signal is one that looks like this function, but narrower in. But I don't want to get this extra repeat going on here. at the Nyquist frequency because that's part of my principal range. I'm gonna see that. I don't want that extra copy in there. Here's another example. If I had a sort of almost like a sinc function here, or in this case it's a sinc squared because it's a triangle function's frequency response, or the inverse transform of a triangle. So we see 3 primary peaks and then some little bumps afterwards. If I was going to try to increase the sampling rate by a factor of 5, I'm going to insert 1, 2, 3, 4 zeros after each of these samples. So we get our center sample, 1, 2, 3, 4, the next sample, 1, 2, 3, 4, and so on in both directions. This original signal that looks like adjacent triangles butted up against each other at the Nyquist rate. Again, when we interject those zeros, I squeeze it in by a factor of 5. So what was here at the Nyquist rate now is at frequency 0.1. So we've stuffed in, we've squeezed everything in. We brought a lot of these copies into the range of into the principal range. Now, what I would like is to have just the one center one in here. That would be the appropriate spectrum for one at a higher sampling rate. But I would want zeros going all the way up till we get to the copy at the new f equals 1. So let's take an example. If I had a signal x1 of n that was some x of t sampled at 500 hertz, and I want to upsample that to make it the same signal, but with a sampling rate of 1 kilohertz, 1,000 samples per second. First, we would put in the zeros, put 1 in between each existing sample, which would double the number of samples. But that's not sufficient because now we have all these extra spectral copies in the principal range that I don't want. And in the time domain, I've got zeros where I want some actual values that are somehow interpolated between the existing values. So we would really like those zeros to be changed into the values that would have happened if I had actually sampled at twice the speed. How we do that is first we'll do that upsampling, that zero insertion, and then I'm again going to use a low-pass filter. An ideal, in the theoretical case, an ideal low-pass filter to get rid of those extra spectral copies. And what that will do to me in the time domain is bump up those zero values that I inserted to an interpolated value in between the existing ones. And it's a band-limited interpolation. It's just like what happened in our reconstruction after the D to A conversion. It's going to fill in the appropriate value where those zeros are that would result if my system were band-limited to the limit of the upper range of the cutoff frequency of the interpolation filter. So in the time domain, we take our original signal, we insert zeros in between all those valid samples, and then run it through a low-pass filter, which will then interpolate, raise those zero values to an interpolated value straddling between the ones that were there before, and it has the appropriate values that a band-limited signal would have produced going through, or that would have happened if it had the band limit that we imposed by this low-pass filter. So taking our triangular picture again, and this is using the discrete time radian frequency, so 2 pi is like f equals 1. If we take our original signal, insert a bunch of zeros, which squeezes in an extra spectral copy in here. I want to keep this one. I want to keep the spectral copy at 1 and at 2 and at 3. So I need a filter that's going to keep those ones and throw away the ones in between that I don't want in my final upsampled signal. And if we could create a fairly ideal shaped filter, we would get as a result the appropriate spectrum for a signal, this signal that was sampled at a higher rate. Here's our f equals 1 or our omega equals 2 pi, the sampling rate. Here's the principal range. So we can do both. Downsampling and upsampling both require low-pass filters to accomplish, and I guess it's worth mentioning that this all works very nicely as long as I could create a fairly ideal low-pass filter. And again, we're talking about a discrete time low-pass filter, right? We're going to do our zero insertion, and then with our discrete time signal, run it through a digital low-pass filter in order to do this interpolation. Now, both of those, that upsampling and downsampling, work if you're trying to upsample or downsample by a whole number value. If I want to double my sampling rate or triple my sampling rate, or downsample by a factor of 5, or downsample by a factor of 7 or 11. If you want to up or downsample by a fractional value, like 1/3 or 4/3 or something that isn't a nice simple whole number value, it can be done. It actually requires a two-step process. And it matters what order we do this in. You're going to upsample and then you're going to downsample to get there. We'll upsample by a factor m, downsample by a factor n. But in between those, we need to do all the appropriate things to handle both the interpolation and to make sure we don't alias when we downsample. Well, it turns out if we do these in the order shown, if we upsample by zero insertion, do the interpolation by low-pass filtering, and then downsample by n, this interpolation low-pass filter does both jobs. It will do the interpolation of the zero inserted signals, and it will do the aliasing prevention of the downsampling signal, as long as we choose the low-pass filter's cutoff appropriate for that downsampling process. And if I do that, then I can do actually fractional changes in sampling rate. But you have to do it in this order. If you try to do it in the opposite order, downsampling first, then filtering, then upsampling, it turns out it's pretty hard to prevent aliasing in that case. So, but if you do it this way, the upsampling first, low-pass filtering appropriately, and then downsampling, we can get these fractional changes in sampling rate. Okay. So again, some of this we've talked about back in sampling theory. We looked at it from the analog domain. Now we see what's going on in the discrete time domain with DTFTs. The last important process that the DTFT gives us insight into, and one that you've been seeing already in the 368 lab again, is the problem and the process of windowing. Windowing is the process whereby we take a long signal, maybe even an infinitely long signal, and extract a snapshot of it, a part of it, a finite number of samples out of what is inherently an infinitely long signal. And this occurs primarily when we want to look at a signal spectrum, when we want to do spectral analysis on a signal. We have no choice but to work with part of the signal. We can't wait for the whole signal to come by. We can't collect an infinite number of samples. So I have to grab a representation of the signal by grabbing some finite number of samples. Well, that grabbing of a finite number of samples, basically truncating the two ends of an infinitely long signal, has consequences in its spectrum. If we take those finite number of samples and Fourier transform them, the answer we get is different from if I had taken the Fourier transform of the whole signal. It has to be. And it was that multiplication property of DTFTs that gave us that insight. When I truncate a signal in the time domain, like an x of n signal, if that was an infinitely long signal, if I want to extract a finite number of samples out of it, that's equivalent to multiplying it by another time function that's a series of ones in the range of sample values I want to keep and zeros everywhere else. that we would recognize as a rect function, basically. And so when I multiply my time domain signal by a rectangle function to extract some finite number of samples, the DTFT multiplication property tells me that, and this is the dual of the convolution property, when I multiply in the one domain, I'm getting convolution in the other. So whatever spectrum x sub n had, I'm not going to see that exact same spectrum anymore. I'm going to see that spectrum convolved with the spectrum of this signal that I'm using to window out a segment of my function, of my original function. So when we multiply functions in the time domain, we get convolution in the DTFT spectrum. And since that spectrum is periodic, and both of these functions will be periodic, the convolution that we're carrying out is really circular convolution. So what implication does that have for when we extract a piece of a signal and look at its spectrum, like on a spectrum analyzer? Well, again, extracting a series of samples is like multiplying whatever function, infinitely long function we have by basically a rectangle function. Here's one is shown centered around n equals 0. If I had a causal version of that, it would start at n equals 0 and go to length to L minus 1 if it has a length L. Now, according to that theory, whatever the spectrum of this is, whatever the DTFT of this function is, that's what's going to get convolved with the spectrum of my original signal that I was trying to look at its spectrum. And so we could derive what is the discrete time Fourier transform of a rectangle function if I use the one that's not even symmetric, but actually starts at n equals 0. We would describe that as a sum from n equals 0 to L minus 1 of 1s times e to the minus j 2 pi in f, or in the omega version, e to the minus j omega n. That's a finite summation, which we have a closed form solution for. Plugging it in our exponential for r gives us this function, which we can convert to a form that we recognize as signs in Euler identities by factoring out certain terms. And what we actually end up with here, it's hard to recognize in this form, this is actually a kind of a sinc function. It's not exactly a sinc function. It's like a sinc function, but there's some other things going on here. It's actually an aliased sinc function. It looks like this. It looks like a sinc function, and it would normally be a sinc function, except these spectral copies repeat. So I'm going to get another copy of this DTFT centered at f equals 1, which is omega equals 2 pi, and f equals 2, and f equals 3, and minus 1, minus 2, minus 3. And those tails of the sinc function start merging together and aliasing and creating this repeating pattern that's sinc-like. Actually give it a name. It's called a discrete sinc function, or a Dirichlet kernel. Now, why does this matter? If I take a nice signal and I want to look at its spectrum, I grab off L samples of it, take its discrete time Fourier transform, I'm not going to see that spectrum just of the original signal, but that original signal convolved with this sinc-like thing. And so if you think of like a perfect cosine, 2 cosine omega 0 n, that should have a discrete time Fourier transform if it was a forever cosine. If it didn't turn on and off, if it was just on forever, I should see 2 impulses. Is its discrete Fourier transform. However, that's not what I'm going to see. I'm not going to see 2 nice values of 1 there. I'm going to see that convolved with my impulse my sinc-like function, my Dirichlet kernel. And so I'll see this on a spectrum analyzer. This sinc-like thing with all these extra bumps. And so the characteristic of signals that are truncated is that their spectrums will have these kind of main lobes in the center. They'll be spread out around their actual frequencies, and there'll be these extra side lobe bumps happening. And it turns out that just simply truncating a signal gives you the worst possible kind of side lobes, gives you the most bounces here, because that's like multiplying your function by a rectangular function. And this is the Fourier transform of a rectangle. It has lots of very big high side lobes. Now it has the narrowest main lobe, so that's a nice thing about it, but it's really got horrendous side lobes. That's why when we do spectrum analysis, we use a different window function. And you may have seen and used on your spectrum analyzers Hamming windows or Hanning windows, or perhaps a flat top window. These are generally functions that aren't a square, not a rectangle with a sudden discontinuity, but they're a smoother function, usually sort of cosine shaped, that taper down the window at the edges to 0. And if you take the Fourier, discrete time Fourier transform of this tapered window function, like this one that's showing a Hamming window, you get something that still has a kind of wide main lobe, but very low side lobes, much, much lower than the rectangle function has. And so often that's very desirable for spectral analysis. So oftentimes we will grab a set of data, finite number of samples out of a data stream, and multiply it by a windowing function like the Hamming window, so that its spectrum is a little more representative of the spectrum of the original signal. So instead of having all these extra side lobes bouncing around and you're wondering, is there really signal there or not? Or is that the tails of my sync function? We're much better able to say, no, there's just one frequency going on here at this big peak. So that's why we like windows that have low side lobes. And there's all kinds of windows. There's some of the more common ones are the Hamming and Hanning windows, which are just slightly different versions of raised cosines. Bartlett windows are triangular windows. Rectangular window is no window at all. It's just truncation. A Blackman window is a little more sophisticated cosine window that has even lower side lobes than the Hamming and Hanning, but it has a trade-off. Always the window functions that have the lowest side lobes have the widest main lobe. So which kind of window you choose depends on what job you want to do with your spectrum analysis. You want to use a window with very low side lobes if you may have some small signals nearby to some bigger ones. Here, if we used a rectangular window and truncated them off, we got this spectrum out of our spectrum analyzer, and somebody asks, okay, what frequencies are there in my data? Well, you say, for sure, I got these 3 frequencies. I don't know if any of these others are relevant or not. They could be side lobes of these peaks, or they could be real signals. If you used a window like a Hamming window or a Hanning window, those side lobes are suppressed, and it's much easier to see, oh no, I've actually got 4 actual signals hiding in there. So particularly for the case where you want to look for small signals in the vicinity of larger ones, you want to choose windows with low side lobes. In the opposite case, if you have 2 spectral peaks really close to each other in frequency, you want to use a window with a very narrow main lobe, because it's the width of the main lobe causes these to overlap each other and merge together when you do the convolution. So for 2 spectral peaks that are really close to each other, you want to use maybe even a rectangular window that's got horrific side lobes, but you can resolve and see, yes, there are actually 2 different frequency spikes close to each other. Whereas if you use a Hamming window that has a wider main lobe, they get merged together and you don't see the 2 distinct peaks. So when you need spectral resolution, you want narrow windows. When you want amplitude resolution, when you want dynamic range resolution, so you can see small signals in the presence of big signals, you want a window with low side lobes. We are out of time. We'll leave it at that. We'll revisit some of these again, some of these topics again as we go forward. But next time we're going to move on to Z transforms, which are going to give us a complete method for doing system analysis. We're going to be able to tie the Z transform back to discrete time Fourier transform so we don't lose all the advantages we have for looking at our signals in a spectrum domain, very much like we were in continuous time systems with Laplace transforms. So we'll come back for that next time.